Okay. In this class, we will talk about volume distribution or apparent volume of distribution, and we are still talking about, sorry for that. Okay, and we are still talking about one compartmental model with IV bolus as administration, route of administration. We are talking about one compartment. We are talking about linear kinetic, and we are talking about single dose. Okay, and as we are talking about linear kinetic, so by default we are talking about first order kinetic, right? And those are things that we talked about last time, and we got the equation model, either differential equation model or other terms or other equations of the same thing, in which we said the xp over dt equals minus k multiplied to xp at certain time, and we mentioned that some references would have xp as db and x node as d node. Okay, this is the differential equation in which we said that after rearrangement and integration, we will have either an exponential equation, which is xp at certain time equals x node multiplied to the exponent term. We may have it in ln term, okay, multiplied to the time, or in log terms, node minus k over 2.303 multiplied to the time. Okay, those are the model equation that we will deal with, and we had different graphs, either the rectilinear graph, the semilog graph, or the log transformed graph, or the len transformed graph. And then we mentioned that the same equation could be in concentration terms, right? And I would just write them, even we had them last time, but just let's say as a reminder, we could have concentration measured and the plasma, let's say, or in the biological fluid at certain time equal Cp node. Also in length term, over time multiplied to the time, or log terms multiplied to the time. And then we mentioned that if we want to have this amount or equations in amount term, and then change it to concentration term, where we're using the equation that the concentration equals the amount over volume. Okay, and we mentioned earlier that to do so, we need to have a constant volume that is not changing over time. Okay, so that volume in kinetic in this case, under those, still we are under those terms. Okay, we call it a Berendt volume of distribution. And why we call it a Berendt volume of distribution, which is as a term or as a symbol is called VD, because it's simply not a physiological volume. Okay, because it's not a physiological volume. So it's not, that's why it's called a Berendt volume of distribution. Okay, that's why it's a Berendt volume distribution. Okay, why is this, or how we can understand this point? First of all, you can find the sentence in your slides that the volume distribution, if we will have it in terms of the concentration and the amount that we have it here, concentration, I would write the same equation here, but in our um, uh, symbols, okay? So concentration measured in the plasma or in the blood equals amount measured in the body over Vd. So this is the amount, this is the volume, a Berendt volume distribution, and this is the measured concentration of the drug. Okay, and for sure this is amount of the drug. Okay, so if we look at this, we can notice that the volume distribution is giving me a relationship between the concentration measured and the amount of the drug in the body. So that's why it's a proportionality constant, that the purpose of it is just to relate the concentration that is measured and the systemic circulation and the amount of the drug in the body at certain time. So this is true at certain time. So it's a math factor or proportionality constant that is relating what is measured in the systemic circulation with the amount of the drug in the body. Okay, so again, this is true at certain time, which means that if we are talking about the initial amount in the body, so we need to use the initial concentration, right? Let's just change it first. At time equals 0, time equals 0 over volume distribution. It's the same as concentration and the initial concentration equals the initial amount over Vd. Okay, as we are talking about IV bolus administration, and if we go back to our equation, our model drawing here for the one compartment model, we know, because we are taking the drug as IV bolus, that the initial amount that we have is the dose that we are taking as IV bolus. Okay, again, this is your initial measured concentration, or what we have at time equals 0. This is the dose or the initial amount of the drug in the body, and this is a Berendt volume distribution. Okay, the idea is that before we were able to determine the initial, if we are having the profiles in terms of amount, we were able to determine or to have or calculate or extrapolate using the profiles to have the initial amount. Can we do this? if we are having it in concentration terms, yes, we have, and we said you can do the same thing you did before for the amounts, but for the concentration. And I will do it very fast, but you had it before in your last videos, okay? So if we are talking about concentration term, it depends on the profile that you are having, or the graph that you are having your profile on. So I will have this rectilinear, semilog, rectilinear, and semilog, okay? And again, I will use the IV bolus one compartment model equation, okay? But I will use it in concentration terms. So I will use the equation that we have, the equations that we have here, okay? I will not rewrite them, but you will have them here as graphs, okay? So model equations using concentration, okay? So we will have concentration versus time, concentration versus time. We will have log concentration versus time, and we will have len concentration versus time. Again, the only difference between this and this profile is the graph that we are using, okay? And the only difference between this graph and this one is the log transformation. The only difference between this graph and this one is the len transformation, okay? So let's go and draw it for each one of them. I have the first one, which is the exponential, okay, because it's on rectilinear. This one, it's semilog, so it will seem visually for us that it's linear. This log transformation, it will be linear, and this len transformation, it will be linear, okay? So the shape of the profiles that we have here, let's just number them: 1, 2, 3, and 4. So the shape that we are having in 2, 3, oops, sorry for that. The shapes of the profile that we're having in profile number 2, number 3, and number 4 is the same as shapes. They are linear, okay? But we mentioned that here we are just visualizing it as linear because we have linear kinetic, but the reality of the profile is what we having on rectilinear profile, which is exponential. And we said that according to the concentration terms that we are having in the equation, we will have the y exponent, the y intercept as Cp naught, which is the initial concentration that we have, and the same thing will be here, which is Cp naught. Okay. For the log transformation, it will be the only difference that the y intercept is log Cb naught rather than just Cb naught because it's in log terms, okay? And the only difference here, it will be len Cb naught because the the y-axis is len terms, in len terms, okay? So if we want Cb naught as the profile in on rectilinear graph and just Cb versus time, it will be just Cb naught. Or in semilog Cb versus time, it will be Cb naught only. If it's log the transform to log, the y-intercept will be log the initial concentration, and in the len will be len the initial concentration. So if you want Cb naught here, you will have the anti-log to get CB node here, and if you want the CB node here, you need to have the anti-len for the CB node. Okay, and we get this earlier, and we understand this already, and we comprehended it already in our previous lectures, but just as a reminder again. So I can have from the model that I have, from the data that I have, as a concentration measured at certain time point, whatever the way that we are presenting our data, whatever the profile that we are using, we can determine CB, the initial concentration that we have, and we know our initial dose, right, that we are giving, so we can determine the Barron volume distribution of the drug. And as I mentioned, it's a Barron volume distribution, and it's not a real physiological volume. And I will just explain this in a minute in an attempt to understand why we call it a Barron and why it's not a physiological a real volume. Okay. And we know that we also have a difference in the slopes here. The slope here will be minus k over 2.303, and the slope here will be minus k here because of the differences in the transformation of the y-axis. Okay. So let's talk a little bit about the concept, the volume of distribution concept, or a Barron volume distribution concept. Okay, let's consider that we have two beakers. Okay, I will draw two beakers with the same, I will consider them with the same volume, but we don't know the volume. Okay, so we have, oops, it's not a good beaker. Beaker number 1 and beaker number 2, or just let's have it as beaker A and beaker B. Okay, so we have them as two beakers again with equal but unknown volume. Okay, and we will have them filled with water. Okay, and let's still use the same color here. Okay, so we have water inside. So we know for sure that both of those beakers have the same volume. Okay, the same volume of water, but we don't know how much. Okay, then we will add in beaker B a small or a little amount of charcoal. Okay, so let's have it as added here. Okay, and we know that charcoal is absorbing agent. Okay, so this is one of the differences between two beakers for now. Then in both beakers, in A and in B, we added the same amount, the same equal amount of potassium iodide. Okay, so we added here and we added here, let's say 1 gram of potassium iodide. And the same thing here, 1 gram of potassium iodide. in both of them. Then what we did after that, we took sample from this beaker and sample from this beaker, okay? And we measured the concentration of Ki, okay? So, and by the way, the concentrations in both of them, in beaker A, let's not use it as here, in A and B, okay? When we measured the concentration, first of all, according to whatever that we have as, or whatever that we know for sure as concentration equals amount over volume, we know if we are talking just by math, and by the way, this is a common sense example, but if we're just talking about the volume that we have in both of them, it's equal volume. And if we are talking about the amount of the potassium iodide in both of them, in both of the beakers, it's the same amount. So, but when we measure the concentration, we have here concentration that is, let's say, as an example, 100 microgram per milliliter. Okay, and in here, 50 microgram per milliliter. Okay, so the concentration of potassium iodide in here is larger or higher. Okay, if you want to back calculate from here, if we are having 50 or 100 as a concentration, and we know the amount that it's 1 gram for sure, we can determine or back calculate the volume of the that we are talking about of the liquid, right? But we will have here, if you do the back calculation as 10 liter, and here you will have it as what? As 20 liter. So if we are talking about the volume, even we are having the same equal volume of water in both of them, on both of the beakers, we are having larger volume here with lower measured concentration of the Ki. And this is a simulation or a symbolic way to understand the burn volume distribution that we have in kinetic. Okay, how is that? Okay, why this happened? First of all, if we know whatever is happening to potassium iodide and water, we know that it will be ionized because it's soluble in water to its ions, right? And we know again that charcoal is absorbing agent, so it will take, or some of the potassium iodide will be absorbed on the charcoal. Okay, so we are losing some of the potassium iodide. Okay, and when we did the back calculation, it gave us an idea that the volume is more, not because the actual volume is more, but because when we have concentration equals amount over volume, we know that the if the concentration is higher, then the volume is lower with constant amount of the material that we are measuring. Or if the concentration is decreasing, the volume is increasing, again, if we are talking about constant amount of the material. So this is what is happening and the model that we are talking about. And again, it's just a symbolic way to understand it. if we are talking about the body. Okay, so the beaker either here or there is simulation of the body, and the water is the biological fluid that we are talking about. Example, as an systemic circulation, we are having drug, right? And we are having different tissues and organs. So this is the way. In both of the beakers, we know that the physiological or actual volume is the same. But the difference is that sometimes the drug is distributed to different organs and tissues. So the volume that is measured, which is again apparent volume, not the physiological volume, is larger. So in this case, we know, according to this example, that the volume distribution is a property of the drug rather than the exact biological system. And in addition, it's also giving us an idea of the distribution of the drug. Okay, so, and again, the more the drug is penetrating or going or distributed to different tissues and organs, it means that the smaller the concentration of the drug or the material that we are measuring in the systemic circulation, and the higher the volume, the measured volume distribution, because it's giving us an idea about the distribution of the drug. Okay, and again, it's why it's not physiological, why it's not actual real physiological volume, because if we are talking about this in numbers, we have certain fluid compartments in the body, right? And those fluid compartments, they are we have ranges that we know from the literature. So if we are talking about let's say adult male with 70 kg weight, we know that the plasma range as a volume is usually around 3 to 5, okay, liter, okay, or 3.5 to 4.5 liter, it depends. So if we are talking about actual volume, we shouldn't have a smaller, sorry, volume than the plasma, which is usually the case. But if we are talking about different compartments, such as let's say plasma, and then intracellular fluid, extracellular fluid, and total body water, and all the compartments, we can have this as around 42 to 45 liter. Okay. So if we are talking about, again, actual physiological volume, then our volume distribution, whatever the drug, should have the range between 3 to 5, minimum to maximum 45 liter. But this is not the case in the kinetic. Why? Again, because the volume that we are having as a number, it's a apparent volume, and it's just a factor that relating the concentration that is measured in the systemic circulation with the amount of the drug in different tissues and organs. And again, this is the, we are still talking about one compartment IV bolus and single dose. So it's the simplest way to talk about the volume distribution as a concept. And we can just think about it about, let's say this is the membranes, whatever, again, simplification of the membranes that we are having, or we need to pass to get the drugs and different tissues and organs. Okay, and we have here the systemic circulation. Okay, so according to the concept that I just mentioned, let's say that again, regarding the distribution, and this is just a simplification of whatever is happening, but it's a way that could help you to understand again what I just mentioned as a concept. So let's say the drug is highly, let's change the color. The drug is highly hydrophilic, or as the let's say we are increasing the hydrophilicity of the drug that we are let's say synthesizing. So it means that the transportation or distribution of the drug through membrane, different membranes, let's say, okay, would be less. So um, accordingly, the volume distribution measured would be less as the hydrophilicity of the drug is increasing, right? If the lipophilicity of the drug is increasing, okay, it means that the distribution of the drug, it's again as simple as we as a concept, as simple as we can talk about it, and still we are talking about first order or linear kinetic only. As the lipophilicity is increasing, and we will talk about this just at the start here, and we will talk about it later because we have some exceptions for that for sure. So if the lipophilicity of the drug is increasing, then the drug is distributing more through membranes. So the volume distribution would be, the apparent volume distribution would be increasing. And again, let's say for the same individual under the same condition that we are having here, but we are just changing the drug. Okay? Another thing, if we are talking about drugs with in a higher plasma protein binding. Okay? If the binding at this site is higher, it means that the transportation or distribution to tissues and organs is less, which means that the volume distribution, measured apparent volume distribution, would be less. Okay, if the tissue protein binding is higher, okay, which means that the drug would be there more, right? So the volume measured volume distribution would be higher. So this is like again in examples telling you the same thing over and over again. First of all, which is very important, first of all, it's apparent volume distribution. It's not real. It's not a physiological volume. And more importantly, it is a drug related property. Okay, so for let's say drug A, the volume distribution in the same body is different than drug B, is different than drug C, is different than drug D. So I hope with this we got the idea about apparent volume distribution. So we can just from now on, when I just say that the concentration measured in the plasma equal the amount and the body at certain time over apparent volume distribution, we know for now that we are talking if again under the condition that we are talking about first order kinetic, that we are talking about constant apparent volume distribution, that it's drug related and drug property, that it's not physiological, and it's apparent volume distribution, and it's just a factor that we are using to relate those important two terms to each other. And I will stop here and I will continue later.